One obvious question that you have at this point is, why do we even care about having this multiple representations? Well, it turns out that this is very common, right, in large software projects. And the question is why? Well, it turns out that there are many reasons. One reason is because the large projects have long lifetimes, right? So as they move on, the project requirements change, okay, over time. And after a while, people add more stuff, right? And sometimes it's also because the single representation is not suitable for every purpose. All right. In the next few weeks, we will see some examples in class where we have different representations for different cases, right? And sometimes because the different programmers work in different parts of the project, right? And they just happily do their own thing, you know. At some point, realize, damn, you know, some people have done the same thing again, right? Therefore, you must actually figure out how to manage the different representations when they coexist. Okay, we'll talk about this in more detail in the next lecture, but for now, we'll just give you some overview, okay, to understand what the issues and what the strategies that you can have, okay, and which are the pros and cons that you need to understand for each strategy. Okay, so let's take a look at a simple example, which is the complex arithmetic package, right? So if you recall, these complex numbers are these imaginary numbers, whereby there's a real part and its imaginary part, right? And imaginary part is the square root of -1. Okay, so typically it's represented with x plus ij. So they have this kind of a imaginary number plane, right? And x plus iy is what you call a rectangular form, right? There's also a polar form, which is of the form x plus iy is r e to the ia. Okay, don't worry too much if your math is not good, give back already, but just know that this exists. Okay, and you can imagine a world whereby there are programs that use the complex numbers, okay? And in these programs, you can use add, subtract, multiply, and divide complex numbers. And I guess what you have is that you also have a complex number package, okay? And in this package, there are two representations. There's the rectangular form and there's a polar form, okay? And it turns out that you need to build this thing, okay, which is the complex number package. And there's a guy called Ben, okay? He has given you this part, and Alyssa, okay, has given you this part, right? All right, if you recall, in lecture 7, we talked about this thing called the rational number package, right? And now we're trying to do this complex addition. So just like in lecture 7, z, okay, if you add z is two complex numbers, z1 and z2. And what you do is that the real part of z is actually the real parts of the two numbers, all right? And the imaginary part is just the imaginary parts of the two numbers. Okay, multiplication is similar. It's actually, but what you do is that you take the magnitude of z, okay, you multiply them together, and angles are also multiplied together. Okay, and these are easily implemented, assuming that you have real part, imaginary part, magnitude, and angle. Okay, and then you can construct. You can use constructors, make from real, imaginary, make from magnitude, and angle. All right, let's first look at Ben's code. Right, so in Ben's code, it's a real, imaginary, xy. So it's a rectangular coordinate. So this is x plus yi. So x is the real part, y is the imaginary part. So essentially what you do is use tuple x and y to keep these two numbers, the real and the imaginary parts. The real part is x, the imaginary part is y. Okay, so it's all good. Now magnitude is actually you do this x squared plus y squared square root. So this is the square root of x squared plus y squared, right? That's what it is. That's the hypotenuse or the magnitude. And then the angle is the arctangent of y over x. Okay, so arctangent. All right. Now to get the same thing from r and a, basically the magnitude and the angle, your x is just r cos a, and your y is just r sine a. Okay. Now for the polar coordinate version, right? So what we can do is that we can store ra instead of xy. So r is the magnitude and a is the angle, right? So real part is just similar to before. Magnitude is now the first thing, okay? Angle is now the second thing, right? So the real part is r cos theta. So again, you take the magnitude, you multiply by the cos. And the imaginary part is r sine theta, right? So this is what you do. So you can get this too. You for xy, where x is x plus yi, okay? You can actually compute r and a. Okay, so you can use the math library to do all these things. So this is the import math, and you can do all this functions, right? Now, whose code is better? Well, it turns out the answer is it depends, right? We'll discuss different representations in the next lecture. Okay, summary. Today we've done a lot of wishful thinking. We started doing game of name. We just pretended we know everything, and then we basically pretended we have all the functions we need, and then we implemented the functions individually. And then design principles, we talked about specifications. Basically, you design a new data structure and you specify what it does. And we showed you that, how you implement data structures, okay? And we also showed you these abstraction barriers, okay, which we showed you in the example of the complex numbers. We'll say more next week. And the last thing to keep in mind is that the implementation affects performance, right? So these are things you should keep in mind for this week. And that's about all for today. It's a long lecture. And if you're very bored, you can play NIM, the dumb version. Then the next thing you can do is you can go and rewrite NIM to allow arbitrary number of piles of coins. Right now you have 2 piles. You can play with 5 piles, 25 piles. And then if you think it's too stupid, you can try to write a better version of computer move that will do the right thing. Right, and that's it for the week. All right, next week we'll start have face-to-face classes. So I look forward to seeing all of you in class. Right, see you soon.